Yeah, I'm ready to start here. You and Annie are chairing this session, right?
Yeah, I wasn't sure. I was here and nobody was.
Everybody's waiting for somebody else to jump.
Yeah, I was wondering what was going on, and I thought that maybe because I did step out the last 2 minutes, maybe someone said that maybe you're starting at 45, but I guess not.
And we're good to go. So why don't you start us off?
All right, let's go for it. So we have three shine style presentations in terms of 2 or 3 slides each with 5 to 10 minutes per speaker, and then we move into a discussion section. The first speaker is Sarah Gibson, and I don't have her title, but I'm sure she'll flash it up in a minute.
I'm going to talk about polarization.
Oh, perfect. Go ahead, Sarah.
Yeah, so I just want to take a few minutes to make sure we are on the same page about what we're talking about when we say that polarization gives us our localization in space, in 3D space. So what we're talking about is, if you think for a moment about a point source, a blob of structure right here, an object, and here's the viewer is looking at it, and this is the sun, this is the sky plane. Okay, so if you just think in an XYZ Cartesian, call this the YZ plane, this is X. And then what happens is we have the 3D position of the object because we can get Y and Z from that sky plane projection. And then X we can get because polarization, so the polarization ratio, basically the ratio of the radial and tangential components of polarization, which can be directly related to what PUNCH is going to measure in terms of polarized brightness, PB, and total brightness, gives you a scattering angle. And then that scattering angle is giving you the out of plane sky plane angle. And then it's just a question of triangles and knowing the distance to the sun and the earth, and you can get the distance in X out to the object. One important caveat to make is that there is a ghost solution due to 2 possible solutions. Basically, you're solving an equation which has a square root. You've got a positive and negative there. And so there are front and back solutions. When you're close in, I'll show you an example. It's pretty straightforward. The ghost solutions are the exact reflection across that sky plane, because when you're close in, the scattering plane, which is known as the Thomson surface, which is basically, the Thomson sphere is really just the loci of all the intersections of the line of sight with the closest approach to the sun, okay? And so when you're close into the sun, that's pretty much just straight up and down, but then it starts to curve out. So let me just show you a couple examples of how that impacts your interpretation and understanding. So in order to take it, because there's another issue, which is the fact that we're not looking at a single blob, we're looking at a distributed structure along the line of sight. So to start getting a feel for how that impacts things, we have this model that I got from and have incorporated into the forward codes from Hugh Morgan, which is similar to the Thénardian model, Poisson type model. Hugh's model also allows for a twist in the structure, which is something we can look at. And so it's basically this hollow croissant of density that's coming out, okay? And the reason that's interesting is it allows us to introduce non-localization in a simple way, meaning that your lines of sight are pointing through, 1 or 2 or more, like for example, the near and the far side of this croissant, okay? So there's more than one density contributing to the polarization ratio, and thus what you're getting out is really a center of mass between these localized structures, okay? So the question is, how well would it do that if you have a distributed structure? So the answer is, when it's close to the sun, pretty well. What I am showing here is I'm looking at this Earth-directed CME. So this is the quadrature view, right, from the side. This is the view head-on towards the Earth. So you're looking at this thing kind of lined up. And what you're seeing is, this is the model. So we have a ground truth density. This is now calculating the position of the density center of mass from the known distribution of density. And then there are the 2 solutions, the front solution and the back solution, that if you just take we forward synthesize polarized brightness and total brightness, like PUNCH can get, and we're taking their ratio and we're using that to get our angle and to get our positions in 3D space and comparing to the ground truth. And again, what we're comparing is the center of mass of the material along the line of sight. And the blue solution, you can see on the right, this is the one we do from our fake data, matches pretty much exactly this solution. You can see it's a darker blue, meaning farther out of the plane of sky. Blue is towards your observer, red is away. It's darker blue, meaning further from the plane of the sky, bigger X, because that part of the little CME is closer to you. Whereas up here at the top, this part of the CME is farther away, so it's a paler blue. This solution, the red one, is the exact mirror image. We all know, I think, from just looking at CMEs that if you have a halo CME, you don't know right away necessarily if it's coming towards you or going away from you, because your line of sight integration, it looks the same if it's close to the sun. And so this is just that ambiguous ghost solution on the other side. So far, so good, so straightforward. It seems quite useful. Now, here's some things we need to take into consideration, though. Oh yeah, so at low elongation, meaning close to the sun, lines of sight are parallel. And so that back solution is just the mirror reflection of the front across the plane of the sky. High elongation, now we've got this thing blowing out, getting closer to the sun. Things aren't quite as simple, because those ghosts are reflecting not across the sky plane, but across the Thomson sphere, which was close, basically aligned with the sky plane close in. So just to show you example of points, so here's the Thomson surface, here's a line of sight that's very elongated. And again, these lines of sight are not parallel. What we're saying, actually, I went a little too fast, is that this, so look at this point here, this orange point. The two solutions are this orange point and this purple point. Okay, that's the true solution if you were just thinking about this little parcel of mass. Here's the true solution for the back point, the nadir, this purple asterisk. This is where it reflects across the Thomson surface. And so things are getting a little bit more complicated, because now what's happening is that your front solution, so if you're down low here, down at the bottom, things are still relatively straightforward, because your front solution is still basically the non-ghost solution down here, because your center of mass distance from the sky plane is represented by that front solution. It's a little bit underestimated, because the inner edge, you see where I'm pointing here, is closer to the Thomson sphere than the outer edge. So in that integrated line of sight integral that you're using, that's essentially giving you your polarization ratio, it's weighted more. So there's an error. Things are a little more complicated when you get up here to the top, because here you're intersecting material on both sides of the Thomson sphere. And you can end up with both negative or positive X. As you can see, the key thing here is that that you're behind the Thomson sphere, and it's no longer about the plane of sky. This is what you get. So this is like that picture I showed you before. This is the ground truth. It's nice and blue. Here you go, dark blue, because further way down here at the bottom. Again, this is the middle solution. It's a little bit smaller, right, up the top, because it's further away, so the perspective effect there, and it's fainter because it's closer to the sky plane. And the front solution is essentially giving you, like I said, more or less the right solution, but underestimated down here because of that weighting effect. But things are getting a little bit, are getting too close to the plane of the sky a little bit than the truth. But compare it to the back solution. This one is going all over the K-place in red and blue, meaning front and back of the plane of the sky. And because of that, you know it's a ghost solution. You have a clue just from the nature of the solution itself that the CME that's coming towards you is in fact in the front. And I'll just finish by telling you that, kind of making that point a little bit more clear. You not only have, you have information that will tell you whether you've got a CME in front or behind, whether it's a halo coming towards you or going away. And in particular, the front solution, so if it's coming towards you, this is what your front solution, which is the right one because it's coming towards you, so it's between you and the sun. Your front solution is going to basically stay positive, and all the points are going to get more positive with time. The back solution starts out negative, and then things get more positive, and then things start to get into this weird, I think it looks like a Russian doll, like a babushka, or one of those little nested dolls. And there's a clear issue here. And in general, the CME is getting bigger. Whereas if you were to go away from the Earth, your back solution would stay negative. That's the correct one all the time. All points getting more negative with time. And your front solution, and remember, you get both of these solutions when you solve these equations. You'd be seeing your basically you'd be seeing it positive the whole time. All points getting more positive. So these two possible solutions will have very distinct measurements in PUNCH. And of course, the CME is ultimately getting smaller. So there's a lot of information there. and a lot thrown at you. But the point I'm trying to make is that some of the information about whether something's in front or behind each other is absolutely preserved in this polarization information. And the reason that's important is because if we have this twisted Poisson model.
Sarah, time mentioned.
Oh, yeah. So in fact, yeah, let me actually land on this one, that the twisted structure, you can in fact get information about what's in front, what's behind, and from that understand whether you have a left-handed or right-handed twisted object. And we can talk more about that if you want. I have another slide with gamma if you want, but let me stop there because there's a lot.
Okay, so the next we'll leave, just like the previous session, we'll leave all the discussion for the end. Let's move on to the next speaker, which is Bernie Jackson. Bernie, are you there and ready to go?
I'm here. So if I can share my screen here,
Perfect.
that'll work a little better maybe. You get this screen shared?
Yeah, you just
Okay.
gotta blow it up.
And I'll get it into this mode.
Yeah.
So anyway, this is a 3-slide presentation, and so you can see here what I've been doing. I've been using this 3D reconstruction that I have to used with stereo data, and in this case, this is our archival data set, and the stereo A was over here, sort of away from the sun, but you can see how much stereo sees in the ecliptic plane in this ecliptic cut. And the resolution here that's seen in situ at stereo for a little bit earlier time period is at about maybe a time, has about a 3.5 hour time cadence in situ. And you can see how it fits the stereo A in situ data quite well at this period for an event that came by and had a density enhancement of about 15 particles per cubic centimeter at stereo A, which was over here on this to the west of the sun-Earth line. But it could see the whole region, and we could reconstruct in this 3-dimensional tomography fitting procedure that I have the different structures. And here's a little later time, you can see this dense structure that actually passed to the north of Earth in this meridional cut, and you can see a void area where the Earth was. And I was very much interested in that because over on the in situ measurement at Earth, you can see that it would reconstruct that pretty well in the wind data. The dashed line is the model that is reconstructed, and the black line is stereo A. And I show you here stereo A in much higher resolution as this event came through. And this blue bar and red bar here are replicated on the in situ plot from stereo. And you can see where this void was, and it was it had magnetic field in the top plot that was somewhat more, it was somewhat enhanced in this region. So that was probably associated with the void. And if you can believe it, that void extended along the ecliptic plane pretty well behind the CME. These are some of the other features. This is density, and you can see this density that I've smoothed out here to the right. The CME starts here, it comes up, then there's a decrease like this, and another bunch of wiggles, and the velocity goes like this down at the bottom. Anyway, that's the black line here in wind. And so you see, that's, if you believe wind, then you can see that's present. Celios also measured in situ there. And I've shown the same plot, but now with the in situ data smooth, like I did for wind. And you see quite a difference here in the Celios in analyses. And then there's ACE too. ACE was present, and you can see that, and it gives a time series that's quite enhanced that replicates. The void was present in all of these, and so it can be seen. So that's interesting, and like I say, it seemed to be associated with a higher magnetic field. So I was really interested in this as a reconstruction technique, because it really certifies that you can reconstruct at stereo A, but stereo A is a long way from Earth, and this 3D reconstruction can do pretty well there. So I've gone ahead and now provided a 3D analysis of stereo data in near real time. The analysis can provide a reconstruction from stereo right here, who's right here seen in this ecliptic plot, and you can see Earth here that this is about 3 or 4 days ago, and because of the data latency from stereo, you don't really do a good job at the current time, but you can at least reconstruct what is 6 days before present, a pretty complete view of the region around stereo and Earth. That it translates to and these are fairly low resolution. This has about a 4-hour cadence that's been represented here, maybe more like 6. Anyway, so it's low resolution, it's fuzzy. You can see structure here at Earth in a plot that's just a synoptic map. This is what the in situ data is present at stereo. There are other things here too. There are many different projects. We use interplanetary scintillation velocity to help in these analyses, and this is the model value that's present at stereo A. Now I should have we're trying to get the current beacon data represented here too, but I should tell you beacon data aren't doing very well these days. The densities are down by about a factor of 5, what you would expect at stereo or at Earth, and the velocities right here, at least from what we've got, don't seem to work very well either, or reconstructing. So that's another problem. We have other things. You can see the inner planets here down below, the density structures relative to that in a remote observer view. This gives you a plot of what's present only seen in the in S10 units brightness from Thompson scattering I'll go back here a couple. But it only shows you the structure if you look in the ecliptic plot that's around Earth. It doesn't show you anything that's close to the sun. This is a Hammer-Eitoff display. Velocity perpendicular to the line of sight does better because it can fill in more at this time. That's what we've been doing. This is the current day. This is right now. I took this off, but this is 6 days before present. And so you see the latency has come up here in this case. The in situ measurements go only to about a couple of days later than before present, and 6 days before present, you do fill in quite a bit of structure that stereo can see. This is the meridional cut, and here is a plot of what's happening around stereo from in the stereo view. IPS is below. Anyway, that's what I've been doing. It is interesting. We hope that we can, what it does here at higher resolution is stress the ability of our system to recreate structure in 3 dimensions at really high resolution. We want to
what-
go down to about a 1 hour resolution, and you can't do that except for the multi-node processor system. Been able to do it with archival data with SME, and so over on the right you see this data that we've reconstructed. Okay, thank you. This is the reconstruction at about 1 hour cadence from SME. And what you can see here is this is an ecliptic cut and a meridional cut here. You see a lot of structure down here at 1 hour cadence. You can look at this, or you can see at that little wave there down at the bottom in the meridional cut. This is real data. That's what that bump here looks like in a synoptic map, that thing. And what you see, some of this structure, you see in here in this synoptic map, that's the front of the CME, or a set of CMEs that occurred. And that's what that front looks like, very irregular at 1 AU. So what I've been doing is you've got the Thompson scattering and polarization brightness, both from brightness and polarization brightness here in different things. And for PUNCH, what we're trying to do is use some of the SME data, at least right now, to provide the tracking system with polarization brightness, a simulation. And we'll get there, we hope, to do this fairly soon. There are lots of nits that are used in this tracking technique, and we think we can probably use that to determine where things are in 3 dimensions. Thanks.
So the next talk is Phil Hess. Are you there?
Yep. Let me see if I can take over sharing.
Mm-hmm. Yeah.
Okay, is everybody seeing that?
Yep.
Okay, so for those of you that don't know me, I'm Phil Hess from the Naval Research Laboratory. I've been doing a lot of work on the WSPR and Solo High heliospheric imagers on board PSP and Solar Orbiter respectively. So I wanted to present this one event that we saw in Solar Orbiter earlier this year as sort of an idea of where we're at with heliospheric imaging right now, and I think some of the gaps that I'm hoping PUNCH will be able to help us fill once we have that data. So for those of you that don't know, since Solo High data hasn't really been that widely distributed yet, it's a 20-degree field of view heliospheric imager composed of 4 individual tiles composed in this mosaic format, which is why in this movie on the left, you see this kind of cross pattern in the middle. This CME from February 23rd was the first CME we saw in sort of a quasi-synoptic mode when we had all 4 tiles running at any kind of a good cadence. And when we first saw the data, it was really interesting. I mean, we didn't have it in this fine of detail. Guillermo Stenborg did all the background subtraction to really produce this very good movie. But at first, we just saw sort of a running difference of this very obvious sort of concave, complexly evolving CME. And it really interested us, and we wanted to do some more with it. So in the big debate we've kind of been having with it is whether this is just sort of one CME that goes off and interacts with the streamer belt and sort of gets deformed as it's erupting, or if this is actually sort of multiple blobs going off and, you know, behind the main CME and somehow sort of coupling with it and creating a more complex structure. So we also saw it in LASCO, and in LASCO, you just sort of see a very standard slow streamer blowout lifting off, going out into C3. And if you look carefully towards the outer part of the C3 field of view, you can see some of the same sort of deformation, but not nearly as striking as we can see it with Solo High. For reference, the Solo High field of view here is the inner field of view is about 10 solar radii, and it goes, and in the extreme left is about 75. This diagram on the bottom is the relative location of everything. So based on my best estimate, this thing went off pretty close to 90 degrees from solar orbiter. From LASCO, it's a little bit behind the plane of the sky, but they're really seeing this same event from two very different sides. And I guess before I go on, what would be very nice for this event in the future would have been if we already had PUNCH sitting here at Earth to get that sort of extended higher resolution heliospheric imaging to see this from the other side and get a much better idea of what was going on. So this just kind of is just another way of showing what you should really be able to take away from the movie. But, you know, I did a simple GCS reconstruction just based on the LASCO data. So take that with a big grain of salt. But again, the velocity profile and the height profile looks very sort of standard streamer blowout. There doesn't look to be anything that complex or unique going on, except if I make JMaps out of the Solar High data, you know, the main propagation happened pretty close to the ecliptic and the streamer belt. And yet for some reason, 20 degrees to the north, the speed is noticeably higher. And it's just another way of showing that same concave complex evolution. So one of the issues we've had so far with all the events seen by both probe and solar orbiter is, you know, really the lack of sort of comprehensive data. We get a lot of events where, you know, you see them well in a heliospheric imager, but obviously if you're seeing well in a heliospheric imager, it's not going to hit the in situ spacecraft. You need to get very lucky in your configuration of different spacecraft to get, you know, the in situ in one, the remote sensing in the other, and just having, you know, that better heliospheric imaging at Earth. Because I think, you know, going back to this movie, all the complex evolution is going on in this sort of, you know, outer coronagraph, inner heliospheric imager field of view, where I think PUNCH can really do a lot of legwork in providing us better observations of the area where, at least in terms of interplanetary propagation, I think most of the interesting physics is happening. And that's why, you know, for now, we're just trying to fill in this gap with models. We've got Christina Kay running some of her models on this to see if we can figure out what's going on with this event. But really, I think the best thing we need is more data. And so we'll do what we can until PUNCH comes along, but hopefully we'll soon have the more data that I think we need.
Okay. Okay. So I think we've done with all the presentations that we wanted to go through in this particular session. We have about 20 odd minutes for a discussion, coming back to a couple of questions that were posed to Sarah by Gilly. Gilly, are you there?
No, I'm here.
Yeah, I think Sarah answered it, but for the general audience here, they might not have seen it. So do you want to pose your questions to Sarah and get a response from her?
So the one that's interesting to me is, you know, are there no spectral lines coming from CMEs, or are they too dim to get some sort of line of sight projected Doppler velocity? Because as someone who's never really looked at a CME at all, but only does mostly spectroscopy, it just kind of seems like if it's going away from you, you're going to get all this, you know, redshift somewhere. And maybe that signal is just even less than the polarization that you're kind of targeting to see. So that's my thing.
Yeah, so I didn't completely answer it, so let me be a little more clear that we're not getting any spectral information from PUNCH on this. I did mention that kind of thing has been done in the inner corona using the comp observations, where you can see from the way the red shift and the blue shift is going as to whether it's coming toward or going away. And also, of course, usually what people do is look for the source to get a sense if it's coming from the front or the back, but that's not always possible. But what the point I wanted to make was that with PUNCH data, it'll be very clear if it's coming toward or going away. Because there's simply, and this has been pointed out by Craig and Tim Howard in the past and others, that that there's the ghost solution doesn't behave in a meaningful way as a function of time. And the way I was doing it with the polarization around the red and blue, it also would give you just it would start to behave in ways that was a clear red flag. This is the ghost solution, and now you can focus on the one and know whether it's going away or coming toward. And so there is going to be information in PUNCH even without the kind of spectral information that you're talking about.
Okay, Gilly.
Oh, thank you.
You had 2 points or 2 questions. Do you want to cover the second one as well? Or
just briefly, I think Sarah addressed that one pretty good.
Okay,
after I posed the question. I was just asking, you know, how do you deal with multiple things along the line of sight basically.
Yeah, and I can follow up a little bit more on that in the sense that we did a test with this structure had this kind of, what we're finding is that a localized structure does a great job at localizing it because you don't have to worry about this distribution. I did a distribution where we had 2 localized structures or maybe 3 along the line of sight, and that created some interesting effects. Again, they can be mitigated by watching the time evolution because of the way things behave with time. A more distributed structure then poses a different kind of problem, and that's something we need to talk about, especially for CIRs. But that's another issue.
Well, and what about like the blob stuff that I showed earlier? If you've got blobs coming off the sun, sort of radially in all directions, are they, that's much lower in intensity overall by a lot than the CMEs are. But like when you're looking at just those dim things, do you think that's gonna be more of an issue?
So it's a question, of course, if they're too dim to see, we won't be able to see them. But if we can resolve, but we have an incredible sensitivity with PUNCH. And so I expect we'll be able to observe some of those. And the way they behave, there'll be the question, if you have multiple blobs along the line of sight, how do you interpret that? But again, if they're moving radially, you don't have that same multiple blobs always along the line of sight. So there's information there. I wonder if this is something that Craig might want to comment on.
Yeah, because it's very much that green plot, will you be able to have in and out of the board information for that green plot?
I'm sorry, could you repeat the exact question here?
Yeah, so I'm talking about your the one where you do the heavy processing radially and you've got all these blobs flowing out. It's on the front page of the website.
Yeah.
And so you've done a good job figuring out where they are, but with PUNCH, will you be able to know for each of those blobs, is it likely to be coming in and out of the board, stuff like that, or is that going to be way too low?
No, for each of those blobs, you'll be able to. It'll be hard in that field of view, precisely because, as you pointed out, this is a small angle formula, right? So the reason this is so hard to do with just a coronagraph is that the plane of the sky acts like a plane, right? It's not until you break the small angle formula and you get out to where the bending of the Thomson surface matters that you can really distinguish kinematically. I see that Angelos and Bernie have their hands up. They probably have things to say too.
Well, as Bernie, one thing was asked about using spectral information to get the location. And that doesn't work with Thomson scattering just because there's too much scattered light to see a good spectral line. The temperature just sort of at 1,000,000 degrees just sort of washes things out. But there's another story here too, and I worked once to get data from the background solar wind and tried to do that with coronagraph data, and you could see fast and slow speeds of different blobs, but the average came out to be and this was regions where there weren't any CMEs, and it was regions selected for that. It was a polar region, and you could see the flow speed and acceleration that was consistent with what is presumed to be the outward acceleration of the solar wind in coronal hole regions above in the poles of the sun over large expanses. So I think maybe if we can mimic that at a fairly fine scale for small features, I think you probably there are all sorts of small features in the background solar wind. It's not stable like people try to believe. And that's what I was trying to say in my talk. So if you can measure those and you can do it well with a system, you should be able to determine through tracking where things are relative to this this Thomson sphere. Of course, the Thomson sphere isn't a problem when you get out to 90 degrees because everything is beyond that Thomson sphere, and so you can just look at use tracking to determine how far and near structures are at that location.
Okay. And Angelos, you had a comment, a question, or something like that?
No, I was going to give some information in the spirit of my earlier comment to Gilly that there's a very big amount of literature on spectral observations of CMEs from UVCS that have provided really a lot of the key information that we have about the internal structure and the thermal profile, which is what I was going after, what I was sort of implying when I said about the energy balance in the CMEs. The UVCS observations have opened up a big issue about what is the thermal, how much thermal energy is deposited inside, or the energy anyway is used up inside the CME as it leaves the corona. And this is something that neither PUNCH nor the other missions that we have is going to address. So all we get from PUNCH or the other corona depths is just kinematic and morphological measurements, and that's about it.
Okay, so there are a couple more questions. One from Ritesh Patel to Sarah. One from Shayla Jones to Sarah. I don't know which one you want to take. Is both of them around?
Shayla's is right on top on the screen right now, so that's
Yeah.
one. To take.
Okay, let's take that one first.
So it's a really interesting question about whether it'll be harder or easier with a real less symmetric CMEs. And it's a great question because you're recognizing, Sheila, that it doesn't necessarily mean it's going to be harder. And I would argue that, in fact, the structure I used was a very smooth structure so that the front and the back had the same mass in it. If you have something which is, if the CMA itself is more localized, if you have a bright front, a dense front, it's actually going to be easier to localize and track. If, however, it's just very complicated along the line of sight, then you are going to have the issue of having to understand that what you're looking at is a weighted line of center of mass type measurement, and one that is affected by how close each piece of mass is to the Templeton sphere. So that makes it more complicated. But I think there are definitely going to be cases where a more complicated CME, a more realistic CME is going to be easier to track because of its asymmetry, if you will.
Okay, so the next is by Ritesh Patel. Did you want to ask that question, Ritesh?
Hi.
A
Yeah.
reminder, just raise your hand.
Shall I
ahead.
go ahead? Yeah. So yeah, I was wondering that since you were discussing about the Doppler shift can be used to see whether a CME is coming towards you or away from you, but at the same time it is also expanding. So if that is also contributing to those shifts, then how that ambiguity can be resolved?
That's a great question. And I was a little confusing before because I mentioned another telescope, and the COMP telescope, which has looked at Doppler shifts. But PUNCH won't be doing that. PUNCH is going to be using the polarization to measure the front location to get a sense of the expansion of the structure in 3D space, for example, or the substructure and the location of that. But you're right, there are issues with Doppler shift, and you can even have situations where the lines, you'll Doppler shift right out of the line, and that's going to impact your measurement. But that's kind of, that's not what PUNCH is going to be doing.
Yeah, okay.
Yes, so there are a couple of comments and questions. One is, I think Craig has a comment, I think, or a question. I'll just bring it up to you, Sarah, and see whether you have addressed that directly.
Yeah, and I
think it's an internal question that you can.
Well, it's just basically a question. It's worth.
I think it's similar to what, yeah. Okay.
Do you see that? Am I?
Yeah, I just see your response now. Okay.
I think it's been discussed.
Yeah, okay. So two things is there was a question from Judy Carpenter to Craig, and I think Craig can answer that in, or we could all saying, is PUNCH going to have, Judy can ask that question if she has the unmute ability. But yeah.
I can speak to the question itself.
Yeah. Space weather and PUNCH, basically.
Sure. So PUNCH has no formal requirement on latency from camera to ground. And as a result, we're not a space weather mission. NOAA have asked us in phase C to develop the capability in the SOC to process data products with low latency. And we also did a trade study during phase B about whether the flight assets could actually support more ground passes to provide real-time data. It turns out they can. And so NOAA may ask us to switch to a mode in which we do one pass per orbit, about once every 90 minutes, instead of one pass per day. If we do that, we'll be able to provide space weather data from either just NIFI or from the WIFIs as well. Not with the same quality as the science data that comes about a week and a half, 2 weeks later, but certainly good enough to track fronts.
Oh, thanks a lot, Craig. Yeah, Ante was asking me about that yesterday. I guess he remembered from some earlier incarnation that that Punch had discussed doing a real-time beacon. So it sounds like NOAA, if you're able to comply with NOAA's request, there will be maybe every 90-minute takes of what's going on.
Yep. So we designed the instruments to operate during passes, and there's a trade-off between pass length and how many there are. So it turns out the spacecraft can support it. It's just not part of our plan right now, but may well be.
Thanks.
Okay. Noor, did you have a comment or a question for?
It's a comment, a question to Sarah. And by the way, I missed most of today's meeting. I'm sorry. Probably this was addressed, but I was not here. So Sarah, when you mentioned COMP and you mentioned obviously PUNCH and other observatories that are observing further out, don't you get the impression that the behavior of CME lower down is quite different from their behavior further out from the sun? And if it is the case, how we are going to basically link the two together?
Yeah, it's a good question. It actually connects to some of the conversations, I guess, I don't know if it was yesterday or the day before. Well, first of all, the mention of COMP was mainly to talk about distinguishing front and backside CMEs and what you could do with Doppler. But in general, you're right. How do you make those connections? And then we have to, there are a lot of great observations out there. We've seen in the stuff that we talked about, I think it was the first day, that the EUV images can go out nearly to 3 solar radii. So we can make connections in that way. And of course, there's other existing middle corona observations, but we need to bridge that gap. Does that answer your question?
Yeah, definitely. Yes. Yes. Thanks.
Okay, so we have one more from Joan. Are you there, Joan? I can't see if she's there. Maybe she's not there. Okay.
If you are a participant, just raise your hand and I'll be able to unmute.
I think that's one also that Craig addressed in an earlier question.
Joan.
So maybe Craig should take this one.
Sure. Yeah, the question that's on everyone's mind here is that the F corona is not unpolarized. It is in fact polarized, and that is a potential issue for any polarizing mission. Fortunately, it's something we've thought about right from the start. And so the strategy that we adopted is to treat it as two separate coronae. So we subtract the radially polarized F corona and separately subtract the tangentially polarized F corona from the two different sets of K data. That is a solution that again raises some questions. So we validated it and demonstrated the background subtraction really works. We can get within about 1% of the K coronal signal in the outer core 2 field of view. So that sort of indicates that that's absolute error. That's not that doesn't account for the similarity in structure between the two different kinds of F corona. So although the F corona is 100 times brighter than the K signal, especially in the outer reaches of our field of view, we can subtract to something to within something like 1 part in 10 to the 4 of it, and that gets us down to a range where we can do 1% or a few percent polarization measures of the K as it propagates out.
Okay. So there was one more question. I don't know whether this sort of discussion ought to be brought back up again in context of the previous comments that Angelos and Craig were having along with Sarah. I don't know whether that discussion is addressed or I think this is related, but I'm not 100% sure. It covered all the topics and I don't have access to that. I have to scroll back and forth. But there was one question that Christian Mostel had for Phil Hess, which we should ask before we wrap up this session regardless. Christian, are you there? Okay, if not, then I can ask the question. Phil, are you still there?
Yep.
All right, so let me just elevate it. Okay, so the question is, what fraction of time is Solar High roughly turned on? And that's probably a very simple question for you to answer.
Right now, the answer is not often. We've had about like 3 different windows where we're on for a couple of days, mostly doing calibration stuff. November is when we're really going to start picking up. So, but even then, it'll still be up to the different remote sensing windows. So it'll be, passes for 10 days here and there.
Okay, sounds good. Okay, so it was my fault that we started about 5 minutes later or 4 minutes late, but I don't want to take Barbara's time on the next topic. It is time to move on, but I still want to make sure that everybody got the questions, got the polarization topic that Sarah said she would address from the previous session. I can't remember which session 8 or session 7. And if that's the case, then we should hand over the session chair and session discussions to Barbara. I think it was addressed. Whether it was fully addressed or not, that may not have been possible in this kind of forum, but I think we talked about it.
And we also have Slido to continue, so I think we should move on.
Yeah, that's what I said. Barbara?
All right, great. So let's see. So we're getting towards the end. I'm just going to give a little bit of a wrap up and hopefully something that'll inspire people to continue being involved in Punch in the near future. Can you see my slides okay?
Yes.
Okay, all right, great. All right. So first of all, I wanted to talk to you about the HSO Connect program, which I hope a lot of you have heard about. HSO Connect is a NASA program to support the integrating of science activities for the virtual environment called the Heliophysics System Observatory. The HSO consists of all the operating missions that provide relevant data. And it also includes the aspects that make these observations valuable, including ground-based observations, models, and other analysis activities. And so the goal of the HSO Connect program is to enhance the scientific return of the whole observatory network by supporting investigations that innovatively connect them from observations from one or more HSO missions with spacecraft and observations, and also across other SMD divisions and other agencies within or outside the United States. And so the whole point is the connection, making this more than the sum of its parts. And I want to remind you guys, I think most of you have been involved in these, but there are some complementary efforts that are also trying to build these new connections. And I really, it's been a really neat time to watch NASA headquarters try to find these missing links and fill these gaps and build a new field, a new connected field for us. So if you attended the Helio 2050 meeting and are participating in the white paper coordination afterwards in preparation for the Heliophysics Decadal Survey, you probably saw a lot of cross-disciplinary topics where a field that is moving more and more away towards what they call stovepiping, or places where people do their traditional analysis. And so we're moving more towards going where the science is and less towards where we used to be. And that's why PUNCH is a great HSO mission. The U in PUNCH is unifying, working to unify two domains that have traditionally kind of fallen in at least in adjacent but often separately discussed things, and the challenges needed to combine it into a unified view of the solar wind as it turns into the heliosphere. I don't know, a lot of us submitted responses to this this RFI that came out in 2020. It was called Research That Falls in a Gap Between Current SMD Solicitations. And so what they were doing is they were seeking for the NASA Science Mission Directorate. There's a lot of opportunities that people put out to do different types of research, but because these are often concise opportunities that are tied to one domain or the other, there were very important breakthroughs that had potential that kind of fill in the gap between them. And so they got a lot of responses to that, and they are being used to assess the balance in these funding portfolios. And the advisory committees are looking for areas that may benefit from more investment. And there are several HSO Connect program elements that have already been enacted. These are ongoing, and they can continue. There will be continued opportunities that will be identified. The first one that came out was in mid-2019. And this was because Parker Probe was going up, and it was clear that we needed more observations from the ground to be able to provide important contextual information, but also supplemental data. So as Parker Probe came through it, especially the perihelia, there would be more information about where it was going and more scientific delivery, scientific complementary information. You saw Phil Hess showing what it looked like on Solar Probe, but you also saw Phil showing supplemental data sets that showed that CME from other viewpoints from coronal imagers. There was another solicitation that came out in, I had that is the wrong number. Oh, no, actually it is, sorry, it's the right number, but it came out, this solicitation actually happened in 2020, or at least the proposals were due in 2020. This was research to interpret these observations, and between Parker Probe and other HSO assets, and these were data analysis, modeling theory, whatever it was that was to support more collective, consistent observations and analysis between these the assets. Another aspect of the HSO Connect program is the whole heliosphere and planetary interactions campaigns, and the associated data and modeling HSO Connect data and model portal, which is kind of an Amazon.com for type database for people to be able to find activities and resources. The WHIPPY, or the Whole Heliosphere and Planetary Interactions Program, it's an international initiative working on understanding the solar minimum period to understand the interconnected sun heliospheric planetary system. So if we're trying to, and these the campaigns build on these previous efforts, if you've done whole sun month or whole heliosphere interval, we've already had a couple hundred people involved in activities so far, and 700 people on the list that are potentially will be providing data products and be participating in future efforts. They usually work on these intervals are usually one full solar rotation. And so what WHIPPY's trying to do is capture the view of the whole sun heliosphere out to the planet system in a way that's not been done before. And these observations and these combined databases are covering a lot of the domain that PUNCH will be filling in when PUNCH is launched. So it's a great opportunity. Unfortunately, the pandemic caused the cancellation of the first WHIPPY workshop. What we benefited from doing is having just a time for everyone to get together and show, here's my data, here's my model, sit together, just do an assessment of what's there and intercompare and work on getting the intercomparison done. That did not happen. And so, but the second WHIPPY workshop, which is one that focuses heavily on the science that can be done with these intervals, is happening next month. Instead of the data modeling assessment workshop, WHIPPY launched two separate programs to set the stage. The online colloquium series started last spring of 2020 to introduce a variety of research topics and challenges that can be addressed by the campaigns. And also there is an extensive and a growing library of what's called show and tell. These are video tutorials that people prepared. And what the show and tell days did is they released a video, a tutorial on how to use an asset or a resource, either data, model, or interpretation or something like that. And then people ask questions and answers, and then and those are available for people now, so that if they go to use a resource, they have a more clear way to do it. So these web colloquia and show and tell days have been building up to the workshop next month. There's still time to join in. Registration's free. And you have a couple weeks. And so please consider joining in. So you're probably asking right now, what does this have to do with PUNCH? You learned in this meeting that PUNCH is tackling several important interdisciplinary challenges. Again, we're trying to unify the corona and heliosphere, and often a lot of these topics are discussed separately when we talk about especially energetic particles and SEPs. Those are often discussed separately from places where we discuss, let's say, coronal hole physics or something like that. And so it's very important for us to really be able to address the goals of PUNCH, to understand how to make these interdisciplinary connections. The PUNCH mission, the PUNCH science goals, and the Heliophysics System Observatory are all examples of things where together they are greater than the sum of the individual components. So thank you. I think I was going to highlight some talks during this presentation, and even the last three talks that Sarah, Bernie, and Phil went through were just really good examples of advances in scientific problems that need to be addressed or should be leveraged in order to really unite the corona and heliosphere. They're not simple questions, but the breakthrough potential is clear. You've seen examples of efforts that people are doing to not just focus on a scientific topic, but an analysis challenge or the development of something that is needed to be able to address something. The flow tracking focus group is working on adapting methods and developing models to be able to assess what kind of methods we can do to understand the flows in the corona in PUNCH data. And they're doing this prior to PUNCH's launch so that we're ready to go. And we've already done a lot of the background work. Especially the CME working group had really good meeting just recently on to identify and start to hit the ground with some important development. And so what I want to ask you guys is, what other focus topics may require advanced development before PUNCH launches? What things we think would be good to have in place? I saw there was pretty much every scene setter discussed the importance of, since PUNCH does extend all the way out to where a lot of in situ observations are, this important translation between imager to in situ data, or what I want to call photons to physics, is something that spans all of the different areas, the science goals, but is something that is a challenge on its own. Both the flow tracking focus group and the CME group are releasing data and model challenges in order to understand how whether we can trust our measurements and do the extremely important task of uncertainty quantification, which is what must be done for any data set if modelers are going to be able to interpret that data. It's not one thing, it's not enough just to say what you think the value is. Modelers need a window of how reliable that value is, and how likely it is to be within this range versus a larger range. There's also some great discussions on the challenge of taking, this is, again, we have a planar or at least a fixed field of view image, and the translation from that, there are 3D effects, there's aperture effects, and there's also interpretation where we're trying to turn this into a 3-dimensional tomographic model. And so my question to you is, now that we've seen how the wonderful work being done in the flow tracking focus group, I want to tell everyone, most of the people in the flow tracking focus group were not original members of the PUNCH team. These are people that we've, especially our associate investigators, we've welcomed them aboard, and they are really hitting hard on the important challenges to make PUNCH possible. And so this is not something that you want to just wait for the PUNCH team to come up with. We've had great examples of people identifying challenges and stepping up to really address them. We also discussed many important connections between PUNCH and other heliophysics system observatory missions. This is really, and so this is not just in terms of development, it has to do with how do we make our science more robust and use these wonderful, not just the methods, but also the connections to build on this and identify important development that is needed. What do we need, basically, not just with PUNCH, but connections to other observatories that will build PUNCH science. And finally, I was just thrilled to see how forward-thinking everyone is about data analysis, data access and analysis infrastructure. This age of ecosystems is extremely exciting. You heard about the Dan Seaton gave a wonderful talk, and I hope you saw the vision for PUNCH. Alec Engel's Pan-Helio project. This is not just a trailblazing thing. This is not a thing where somebody, sets a trail and you can follow. They're bringing you with them. So whenever you sit down in a data ecosystem, you're not following the exact same steps they did. Those things are already there for you. You can just sit down and drive. So this era of modern data infrastructure not only saves time, combines effort, and combines skills and allows people to benefit, but it also brings in a lot more people that are able to really use PUNCH data to the best of its ability. So thank you so much for participating in this workshop, but I hope you don't think that ends here. I really hope that you will consider yourselves now part of the extended PUNCH community. So many of you identified important new connections, really important challenges. Some of you have already shown us that there are solutions and methods that that are going to be valuable to address not just PUNCH's fundamental science goals, but the greater set of important science that PUNCH can do. And there are a lot of opportunities. So a bright future for PUNCH awaits us. We're very much looking forward to the next PUNCH workshop, but I hope that we will also have some additional task groups and additional discussions for you guys that you guys would be willing to participate in as well. So.
Thank you very much.
Okay, you're there. I was like, sometimes you wonder, like, did my internet drop out 2 minutes into it, and I've just been talking to nothing? All right, good, you're there.
That was phenomenal. Thank you, Barbara.
So let's see if we have questions or comments for Barbara. If you want to raise your hand or put them in.
And I want to invite Sarah and Craig, please. This is kind of all of us together, and so if you guys have an answer, this is about really kind of connecting and building the community. So I'd like to invite you to answer them as well.
Please raise your hand or put something in the Slido if you have a question or comment for Barbara or any of
Well,
us.
not just a question or comment, but I saw Heather just a minute. Heather really inspired us to think about what photons can do for physics. How do you take this image or data and really connect it to understanding in situ measurements? And all the other scene setters have really, Rohit Shibber, did kind of the complementary part of that for turbulence. We saw in the CME and CIR and all these talks, where people were talking about the importance of not just using PUNCH in isolation. So please, it doesn't have to be a question. Please make a suggestion. I think we really want to move forward with these Okay. Yeah. And shouldn't it be photons to particles, not photons to physics? Well, Heather talked about using it to deduce not just particles, but magnetic field and things. You know, these are certainly the CME connections can be more than that. So I like to think photons to physics, not just photons to particles, but in other words, connecting that. So I was just looking at the thing. Yep.
Yeah, this is Heather. Yeah, I just started going through some information on how to like how people are deconvolving and how people are doing assimilations. There are some assumptions in there, but I need to do more of that. So I might be reaching out to people to help me understand more of that, because I think we can update and make some assumptions that are a little better than some of the previous assumptions. So I'm gonna be working on that, but I need help because I'm not an expert on all the image processing.
I want to highlight something that both Heather and Barbara just said, which is just how interdisciplinary and how open we need to be as we treat the science that we're covering with PUNCH. PUNCH, has it right in the name. It's a mission to unify the corona and heliosphere, and with it the communities of solar physics and solar wind physics, right? The kind of stuff that people like Dr. Elliott have been doing is in some ways the inverse of what PUNCH does, right? PUNCH measures large scale structure very well and doesn't really tell us anything about the microphysics of what's going on in a feature. But we need to unify the language of the communities that have been studying these features in different systems and at different altitudes. And that sort of goes for the smaller scale stuff too, right? Image processing itself is something many of us get excited about. Many others of us just sort of, give me some images I can look at, analyze them, right? So we all have things to bring to the table, and I expect to see a lot of collaborative papers come out of meetings like this. I don't want everyone to just go away and say, okay, now I know what I need for my science, right? We are a community, and we will get a lot more done if we remember that we're a community of fellows in the sense of fellowship, not in the sense of men. This works best when we go at it hammer and tongs in scientific debate, but remember that we're all human and we're all pulling in the same direction. So thanks for that great overview, Barbara.
So I'll follow up on something that Barbara raised, which was she mentioned the WUPI and the show and tells that we've been doing. And the purpose there was really to say, okay, if somebody has a data set or a model or something that the community used, to have a nice, simple place where you can go and you can watch a video of that person walking you through how to access, how to use those resources. And I think we really need to start thinking about doing that for PUNCH. This meeting a lot of it was about tools, the tools that we're developing in advance of PUNCH, so that when we get the data, we don't have to sit around making tools. We have them already set, we've already got them tested, we've done some challenges on them, for example. And so what would be really helpful, we talked about maybe having boot camps, right? I think we mentioned like a polarization boot camp. As you could see, there's a lot of issues there. But even in advance of having a boot camp, I think we can start preparing little modules of information about the basics of polarization, or about some of the wonderful models and tools that people have been talking about all week. So it'd be great to get feedback. Can somebody post that survey? Oh, yep, it's in there. It's like three comments back. There's the Survey Monkey. If you do the survey, that you could, for example, in that survey, make a note of, I would really like to see a tutorial on what Raphael Atias showed, for example. I'm just picking out of the hat. There were many that could have been candidates for that. And so we can get a sense of what the desire and the needs are of the community for giving that kind of information, even in advance of doing boot camps. If you want to throw some in the chat, or if anybody wants to raise their hand and mention things like that, I encourage it. But we can also use things like emailing me or Craig or any of the working group leads, or using the survey, in fact, to give feedback.
Mm-hmm. And remember, in the survey, you can make suggestions. One of the hard choices we had was there were a lot of, we sat there looking at the abstracts we received, and they were excellent. And our choice was, do we have a long meeting with a lot of really in-depth discussions where we risk people kind of getting saturated? Did we have parallel sessions where someone could, where you would have to choose which one to be in, and that would be very difficult if we had them at the same time, but it meant the meeting could go on. Or what we ended up doing was had shine type talks where we were hoping that it would stimulate and have more time for discussion to stimulate that interaction. And so we'd like to hear from you guys and know whether you thought that worked out well. I myself, I'll be disappointed if you don't at least recommend a lot of discussion time, because that was very important to me. But you're allowed to disagree, of course. But this balance between bringing in all of the different ideas versus but also having a large group trying to discuss these issues without it taking too long, it's important. We really want to make sure we hit the right balance for everyone at the next meeting.
So I see that Dipankar Banerjee has his hand up. And I want to just take a moment to thank our speakers. I believe we had some speakers today who were speaking from India, and if so, it was probably close to midnight, and I am so impressed. You guys did so great. And I believe, Dipankar, tell us what time it is. Come, go ahead and
It's just,
if you dare.
It's just nearing 1:30 in the morning. And I just wanted to tell you, just along with me, there's quite a few very young people, the graduate and undergraduate students are very excited. I really must compliment you and the entire PUNCH team, Craig, Barbara, Sarah. The format which you have also introduced, I think I'm very much liking it. I was a little concerned about the fast track or Gilly type, the talks, and I see that the younger guys are still really getting into it. But the discussion sessions are very exciting because, there you can really elaborate things, and also things are recorded on the Slido. So I think I'm really, very excited to see this new format. And again, the openness, what you have shown to this early phase of PUNCH mission is really, really very appreciating. And I'm sure that you will see many more young minds from this part of the continent actively working for PUNCH.
Well, we thank you for that so much. And I was so impressed with what I saw today, and
And what better compliment than someone who's up at 2 a.m. telling us that we kept them engaged and interested. That is a huge compliment.
I'm just impressed that Dipankar is still awake. Thanks.
And I'll remind everybody that we will have, as we're reaching the final minutes now, that we will have all the talks and the presentations available online through the online agenda. You should be able to access that easily through our webpage. If you have any questions, please let us know for any difficulty accessing, because there's some great stuff there already in terms of a repository, a place to go look to find out what everybody's working on. Okay, I want to thank everybody. I want to thank our support from CPAS. We had some wonderful people. We had Kelvin, who was keeping everything moving, and Michelle and Tanya on the back end, who was doing our web pages. And I want to thank our working group leads, Nikki and Barbara and Kurt and Steve and Annie and Mihir and Dave. And I want to thank all the people on our SOC and people who have been helping us move forward with PUNCH all along, all of you for coming and participating. And of course, our great leader, Craig, who I want to give, who gets to lead us, training the community, riding his dragon. Why don't you have the last words? And did I forget anybody to thank?
Only the person you can't thank, which is you.
Exactly.
Let's thank
Sarah
Sarah
Gibson,
putting this all together. Oh yeah, go ahead, Barbara.
The best project scientist ever. And I've been a project scientist.
Thanks to our associate investigator. Thanks to our.
I would like to point out that Sarah has organized all of us and put all of this together while also submitting a CSR to another Explorer program, which just presses the living daylights out of me. So well done.
Yeah.
Move forward. Oh, go ahead.
If you guys want, you can go in. Oh, that's right. I guess everybody can't show their video, but I'd like to just those of you who can't unmute or just, nice job, everyone.
As we move forward, we will be having hopefully twice a year tag ups. Once a year we'll do a big meeting. Once a year we'll do a smaller science meeting in addition to the science workshops. So keep your eyes open. We are trying to include everyone in this rabble who's doing relevant work. So if you run into a colleague who might enjoy participating in these discussions, please rope them in. We'll do our best to make it hard for them to leave, and we'll all get some great science done. So
okay, and in the last 30 seconds, Gilly has anarchistly enabled everybody to unmute. So everybody, let's just say together, I'll lead you to say, go punch, ready? Go,
Go punch!
Bye, everybody. Thank you.
Thank you all.
This is a really fun meeting this week.